right, so far we have covered the first principle of thermodynamics, which states what? So the first principle of thermodynamics basically is what? We say is heat minus work is equal to the change in energy. Okay? And for instance, if we're studying any type of cycle, this is the most classic one, so I do this one, but so if you do this cycle over here, it doesn't matter which one you do. Okay? What's going to happen is that you see that you start at one point and you end up at the same point, no? So what does that mean about the changes in energy? If you start at the same height, the potential energy will be zero, no? If you start and end up at the same velocity, the kinetic energy will be zero. If you start and end up at the same point, the change in energy will be zero, no? So really all this term here is zero for a cycle, all right? So then what happens for the cycle? So then what happens is that you have that all the work or all the heat will be equal to so all the work will be equal to the amount of heat, or all the heat will be equal to the amount of work. All right? So this is the first principle of thermodynamics. However, this equation implies two things that are not really true, that, as you might know. So what is the first one? Is that this implies that, for example, let's say you have a steam machine that produces an amount of heat Q. That means that you can transform 100% of the heat into work, no? All right? Or you can transform the work 100% into heat. So there's two implications of this equation. So above equation implies what? So the processes or the process going either from heat to Q or Q to heat is 100% efficient. Okay, that's what it implies over there, no? So now, is this true or not? Or the answer is not true, and we know that. So this is not possible because any thermodynamic process / cycles always operates between two temperatures or two temperature reservoirs. Okay, so I have it red, but we have done that figure many times. So for example, for a power cycle, what do you have? Let's say we have a power cycle. We can do like a review, quick review. We know this one will always operate between a hot reservoir and a cold reservoir. Okay, so let's say this one will be at a temperature TH, this one will be at a temperature T cold. And we know that heat will be going from the hot reservoir into the power cycle, and then some heat will come out of the power cycle and will go into the cold reservoir. Okay? All right, and if you remember for the power cycle, what do we say? What is the efficiency? The efficiency is always whatever you get out divided by whatever you put in, no? All right? So what are we getting out over here? If you do this is a power cycle, we get work. All right? What do you need to put in? Heat. If you remember when we did all the different efficiency for the power cycle, the refrigeration cycles, and the heat pump cycles, we did this figure, no? Yeah. So now the efficiency, this one, so the amount of work you can get, this is basically the limitation like this one, is really limited to what? We know is Q hot minus Q cold divided by Q hot, and this is equal to 1 minus QC over Q cold, no? Q cold over Q hot, sorry. And I even mentioned to you at the time that this you can rewrite it as, for an ideal case, okay, into 1 minus T cold over TH. All right, so you see that this first principle of thermodynamics implies that the work is 100% efficient, that the process, the cycle is 100% efficient, but this is not true. But we were able to overcome this issue by deriving this type of equations. Okay? All right? Now, what is the second limitation of the above equation? What does that equation implies as well? Is that we can write this equation as, or we can read this equation from right to left or left to right. So we can say that you can transform all the work into heat, and then you can transform all the heat again into the same amount of work. Correct? So that only doesn't only mean that this equal sign is 100% efficient, but it means that you can go from right to left or left to right, meaning that it's completely reversible. Okay? So it's not an exact example, okay, if you really look at the definition of thermodynamics, but it's a good example for the understanding, okay? So for example, again, it's not 100% true, okay? But imagine you have water. You can transform liquid water into ice, and you can get back the ice can come back liquid water, no? And you can go through that process over and over. So this will be a reversible process. Okay? Something that will not be reversible, again, is just an example to explain it, but it's not really 100% correct, okay? The other example is like if you burn a piece of wood, a log, you're going to get ashes, correct? Can you get the piece of wood or the log from the ashes? No. So basically, that process will be said to be irreversible, okay? So this equation here, we tell you all the time that all the processes are reversible, but you know that many processes in life are irreversible. Okay? So we also need to take that into consideration. So, okay, so the equation that we take that into consideration is when we do the derivation of the second principle of thermodynamics. So, the equation W equal to Q also implies that the process / cycle is reversible. So basically it means that you can go right to left into the equal sign. However, many processes / cycles are not reversible. Okay, that's what the ones I call irreversible. Are irreversible. So, in order to take into consideration the reversibility of a process slash cycle, the concept of entropy must be introduced. Okay? Okay, I think I know. All right. All right, so page 70. All right, so at this time is when Johnny asks the class, like, what is for you entropy? Okay, and some of you have a general knowledge, but I always get the most complicated definitions. People always tell me it's a measure of chaos or disorder. Okay, which is true, but if I tell you to please give more detail, okay, or get into more detail about the definition, people start getting lost. And it's what I always say, that when you don't really know something, you like to make it look very complicated, okay? All right? But really, it's a lot easier than what you think. Really, the entropy, I hope that we're done by the derivation and everything, is just a measure on how you are using the energy that you have at your hand. I mean, disposable for you to use. So, for example, if you use it in a good way, meaning that you use it and then you can recover it again, that means that the system should be reversible, meaning that you are not losing any entropy, correct? Now, let's say you have a certain amount of energy and you use it in a process or a cycle, and at the end of the process cycle, you don't end up with the same amount of energy that you had at the beginning. So what does that mean? That some energy was lost somewhere, no? So in that case, you will see that the entropy will not be zero, it will have a certain value, okay? So really, what it means, the entropy, the easy definition, I think, is a measure on how well you use the energy that you have available. Okay? So why the definition of chaos is also good? Because, for example, let's say you are here in this room. That's what they say. You know, you are here in this room, and let's say nothing moves. You don't do anything. All right? But what happened if slowly this room starts heating up? What's going to happen? The molecules are going to start to hit each other, no? And by hitting each other, what's going to happen? They're going to start, when there's impact, you have energy that is dissipated on the impact due to the deformation of the molecules, and some of them in the noise, no? If it was like a car impact. So then what's going to happen in that room is that slowly you're going to have the entropy, because you cannot recover all energy. The entropy is going to increase, and increase, no? Okay? So that's what they tell you. It can also tell you if it's an order of disorder, no? Into the room or not. All right? But in order to do that, we need to derive what is the entropy, or at least understand where it's coming from. Okay? So where it's coming from actually is not complicated. We already read it, but I'm going to redo it again. Okay? So this was derived by a French engineer in the early 19th century, around 1824. All right? And in those days, I mean, at least in, all the major advantages come from either England, France, or Germany, Europe, all right? And they were all military because all the I don't know if you're aware, but all the engineering schools were military schools. And they kind of, I mean, they are still a little bit like that. Anyway, so let's just redo the same picture as before. So this is now, instead of calling a power cycle, we're going to call it a Carnot cycle, which is the same thing as a power cycle. So this one is operated between a hot reservoir and a cold reservoir. So you have, and this one is T hot, Q hot, T cold, Q cold. Same figure as before. And what is the goal of the Carnot cycle or the power cycle is to generate work. All right? Okay, so what he did is just this. He said the efficiency here, okay, I'm going to redo it again, is equal to what? Whatever you get out divided by whatever you put in. So this is equal to Q hot minus Q cold divided by Q hot. So now we just rewrite the same equation as before. This is equal to 1 minus QC over Q hot. But now this is also equal to 1 minus TC over T hot. Okay, so if you want this part over here, we correspond to a Carnot efficiency or basically what we mean, this is the ideal case. All right, slash meaning, which means that the system is not reversible, but you will assume that it's reversible. Why do I have that square over there? And this part over here is the general case. That means that is the most common one. That probably is the one that defines if the system is irreversible. Okay, but you see, basically it's the same thing. But now what he did is, this is the whole foundation, okay? What he says is that the efficiency of an irreversible let's say engine, like this one here, or process, is always less than the efficiency of a reversible engine operating between the same temperature reservoirs. Okay, so basically the first Carnot principle is what? That the efficiency of an irreversible cycle will always be lower than the efficiency of a reversible cycle. Okay. This is really important one, okay? Then there's another one, the Carnot second principle, which basically means that the efficiency of the cycle, we might write it down if you want, the efficiency of the cycle does not depend on the working substance. So for example, it doesn't depend if here we're talking about water, gasoline, any gas or anything, no? The efficiency at the end depends on what? On the temperature of the hot reservoirs, and does not depend on the substance, okay? So you want that would be the second kind of principle, but it's not needed for the derivation. But you see, this was the whole thing he did, but then you had a guy that was very smart, Clausius. So I say Clausius theorem or Clausius inequality. So what can I do here? All right, so the Clausius, he used the first principle of Carnot in that 1 minus QC Q hot equal to 1 minus TC T hot. Okay, and what he did is just this. Imagine, I mean, before we did this type of cycle, which is very well defined, no? But let's say we do any type of cycle, so let's say, and this is generally they look like. I don't know if you have those, if you have a motorcycle or a car, and they have the computer to see at the mixer you can do for the efficiency and so on, no? And you look at the figure of the power, it's always some type of circle ellipse, no? It's never something very well defined. But anyway, so he say you have this type of cycle here, this is a general one, and this is here it's the same one. This is let me do here the figure, the Carnot cycle. Let me do the figure here. Now, this is a straight line. And this is a Carnot cycle. Carnot power cycle. All right, so just like you do many times in math, what do you do, for example, to calculate the integral? If you have to calculate the integral of this, well, you will break it into little pieces, the way to do an integral, what you break this into triangles, the rectangles now, and then little triangles, and you end up calculating the surface. So here what he did is, okay, this is my Carnot cycle, which will receive here Q hot, and remove here Q cold, and each one of the little cycles will be creating work, no? All right. So what he's saying is that consider that all this cycle here is operating between a hot reservoir over here and a cold reservoir over here, and each one of these spaces here is kind of a Carnot cycle. So let's say you will have a delta Q hot. This will be a delta Q prime hot. Okay. And let's say this go all the way to the end, and this one could be here, the delta Q sub n, Q sub upper n hot. And then here at the bottom, you're going to have the delta Q cold, delta Q cold prime, and I say this will be here, the delta Q cold to the n, okay, for the n cycle. So if you add all of this together, you're going to end up knowing what is the efficiency for this cycle, no? Yeah? All right, so that's the important part over here. So basically, if we look at the first cycle, So let's say first cycle, meaning that I'm just looking at this one here, delta QH, delta Q cold, no? For this one, what will you get? You will get the efficiency is equal to 1 minus delta Q cold, delta Q hot. All right. And this is equal to 1 minus TC over T hot. I mean, I didn't want to do here too much in this thing, but if you have a figure here, you can say on the top here will be the reservoir. Okay, everything is coming from. At the bottom, you will have a cold reservoir, no? Okay. So all these lines will come from the hot reservoir, like this one here. Hot, cold, no? All right? So, meaning that for each one of these cycles, we can write this part of the equation. This will be the ideal case. Okay, so if we do the math now, what does that mean? You can cancel out the ones, you can cancel out the negative sign, and you're going to end up with the efficiency will be equal to delta QC delta QH equal to TC over TH, or this will just be delta Q cold over T cold. So now just look at the right hand side. It doesn't matter how you write it, just going to write it this form. Okay? Now, for a system, what is the sign convention? Heat going in is what? Positive, and heat coming out is negative, no? All right? So now the heat here, hot, is positive, the Q cold is negative. All right? So now using the sign convention, we can say that you're going to have negative delta Q sub C over TC equal to delta Q sub H over TH. Which means what? Delta Q sub C over T sub C plus delta Q sub H over TH will be equal to 0. All right? So guys, this is the whole thing. What I just did right here, this is the whole concept between second principle of thermodynamics. All right? So now, if we do the same thing for the second cycle, I'm going to go a little bit faster. So which one is the second cycle? Basically, it's exactly the same thing, but this time we're talking about the Q prime hot and the Q prime cold, no? Yep. So basically, we get exactly the same equation. So we have the efficiency should be the same for the cycle. So it will be equal to 1 minus delta Q prime cold divided by delta Q prime hot will be equal to 1 minus T cold over T hot. Okay, I'm going to go a bit faster here. So this will mean that delta Q prime C over delta Q prime hot equal to T cold over T hot. Or this will mean that delta Q prime cold over TC equal to delta Q prime hot over T hot. And because of the sign convention, this is negative. So you end up with delta Q prime cold over T cold plus delta Q prime hot over T hot is equal to 0. Okay, and you have the same for all cycles up to the n cycle. So mathematically speaking, the way to write this is as follows. So you would say that for the first cycle, what do we have? We have delta Q hot, T cold divided by delta Q cold divided by T cold, or delta Q hot over T hot. This is the first cycle, plus the one of the second cycle, Q prime T cold plus delta Q prime hot T hot plus all the cycles up to the n so this is a C. This should not be a prime here, sorry, delta Q and hot T hot. So basically you see the idea, no? All of them, you add them together, they should be equal to 0. Okay? So when you do the summation of each one of these cycles around this surface over here, or around this circle, no? So basically I can just rewrite this equation here, which is the summation of all of them. I can just rewrite it as being equal to the integral. You know that the integral is the same thing as doing the summation. Integral sign is the same thing as saying summation, no? Around the contour, around the cycle of the delta Q sub C T cold plus delta Q sub H T hot, so will be the summation of all of them. Okay? You can do all of them, and this is, what can I say here, plus. So this is equivalent at the end. If I remove, we can say this is equivalent to delta Q over T equal to 0, going around the circle. I mean, here we have to add all of them, and basically you have this ratio. So you say the summation of all the delta Q's over T is equal to 0. But this is for what? What is the assumption that we did at the beginning when we did the division of this one? We use the Carnot cycle, no? Yeah? We say the Carnot cycle is like the ideal efficiency that will correspond to the reversible process or cycle. Okay? So from here we can say that this ratio, if you do the summation of all the ratios of delta Q over T, and they are equal to 0, this will mean that the process or the system is reversible. Okay. Now, using Carnot principle, that says what? The efficiency of an irreversible cycle is always lower than the efficiency of a reversible cycle. What do we have here? And when you look at the derivation we did, the left-hand side, let's see, what is that page? What is that page? Let's see, not here. Here it is. We said that the efficiency for the reversible is in function of the Q's. The one for the reversible will be in function of the T's, no? All right. So this will mean that the efficiency of 1 minus Q cold over Q hot will be lower than 1 minus Tc over T hot. Over here, this 1 and minus sign will disappear, but because of our sign convention, the heat coming out, Q cold is negative, no? Same as before. So now what happens if you put a negative sign now in front of this one? You reverse the order, the direction of the inequality. All right? So this will give you that minus, and I'm going to change the C, I'm going to move the C, minus Q sub C over Tc will be larger than Q hot over T hot. Basically, it's not important the derivation, but this is when you put the minus sign, you change the order of the inequality. Okay? So this will give you what now? That. So this is the reversible side, this is the irreversible side, okay? This side is, let's say, reversible. This is irreversible, so this will give you that Q over C, Tc, irreversible plus Q hot, T hot, reversible will be lower than 0. Okay, again, the derivation is not important. We just derived that the ratio of the Q sub H of the Q over T for a reversible cycle is 0. So this will give you what? That if the system is irreversible, the ratio Q over T for an irreversible cycle will be negative, or you can just rewrite it as follows for an irreversible cycle. So again, don't worry about this part of the derivation. What's important over here is to, at the end, find out what? Is that now we have a quantity, which is delta Q over T, that if this quantity is equal to 0, what does that mean? That the cycle or the process will be reversible, and if it is negative, but just don't think about negative, think about just about different than 0, it will be irreversible. Okay, and this is what is known as the Clausius inequality or theorem. Okay? So from this equation, somebody between Clausius and Kelvin, they define the concept of entropy. That basically entropy, if you look at the etymology of the term, it comes from the Greek, and from the Greek it means how much it is of transformability. Okay? So it means how much substance you can transform. Okay? So the definition of entropy is so change in entropy, where S is entropy, what do you think will be equal to? To what we just calculated, no? From the Clausius inequality. So this is the entropy. So what should be the units? What will be the units of Q? Will be generally units of joules, kilojoules, okay, and this will be probably Kelvin, no? Yeah? All right. So now comes something that's why I'm going to do it now, so we don't create confusion. There's something Kelvin defined, so Lord Kelvin defined the concept of increasing entropy of the universe. Okay, that means what? The total change of entropy the total change of the universe, let's say, will be equal to delta Q over T plus whatever is the change of your process. Okay, and if you want to be a little bit, that's why entropy is one of those interesting concepts that people like to do philosophy about it. So if they say this is define the concept of increasing entropy of the universe. So basically what does that mean is that he states that the entropy of the universe is going to keep increasing, increasing, and increasing, no? So what's going to happen if the entropy increases, increases, and increases all the time? The less energy available you're going to have to use, because the more energy is wasted, no? Okay? So if you want to be very philosophical, that's what they say, for example, what is a black hole? It's a hole where you get all the entropy, no? What is a black hole doing? Absorbing all the energy, no? Yeah? So at the end, if you think about it, what do they think is going to happen at the end with the black holes? Is that they're going to absorb all the energy, and at the end they're going to end up exploding because they're not going to be able to hold on to that much energy, no? All this stuff is based on the concept of entropy. All right? So the concept of entropy of the universe means that the entropy of the universe keeps increasing. Okay? So always be, higher or equal to 0 if you want, no? But will always be increasing. All right, so from the concept of increasing entropy, and this is now, we need to be careful because this is what is used. So from above concept, we can rewrite this. Now, if the change of entropy of the universe is equal to 0, we can say that that process or cycle will be reversible. If the change of entropy of the universe is higher than 0, we say that it will be irreversible. It's a lot of material today, yeah? All right, last thing was material was speaking, but this is just the one that creates confusion when you do a calculation. Term delta Q over T. Okay? So let's say you have here a cycle or process that is operating, okay? And this cycle, here this will be your system. But this one can be operating here, let's say at a reference temperature will be outside. No, this T reference could be what? Could be the hot reservoir, could be the cold reservoir, but could be any other temperature as well, whatever you want. So now let's be careful because what is the sign convention for heat? Heat coming in will be positive, heat coming out is negative, no? Yeah? So this term over here, what will happen? If it is delta Q, so let's say T reference, if it is delta Q hot over T reference, this value will be positive, no? Yeah, does that make sense or not? What happens if you have a system, nobody's acting into it, and now you put energy into it? What's going to happen? The molecules, you're going to increase the temperature, the molecules are going to start hitting each other, no? You're going to increase the entropy of the system, no? Yeah? Now, what happens if the heat is coming out? So if you do that, the Q out, so if you want, this will be the Q hot, let's say it will be the Q hot. But it doesn't mean it's Q hot, Q cold, it's just to make the difference. But now, if you look at the delta Q cold over T reference, now this Q here is negative, no? Which means that this term will be then negative. And this term over here defines whatever is happening inside here. Okay? All right, so enough theory. Let's do a problem. Let's come up with a problem. Okay, so over here, let's make up a problem. This is the most classic problems that I can think of. So page 74. So let's say example. So in here, imagine that we have a tank that has some type of valve in the middle. Okay, the water can circulate from one side to the other. All right. So now, let's say that on one side you have hot water. Okay? What could be the temperature of the hot water? Whatever. I'll make it up, 80 degrees Celsius. Okay? And let's say on the other side you have cold or fresh water, let's say cold. And let's say you have what temperature you want, let's say, whatever, 15 degrees Celsius, okay? I'm making it up. So now, if I ask you, if it's the same quantity of water on each side, if I tell you once you open the valve, what will be the temperature of the mixer? Probably you would just say it would be 95, so it would be 47.5, no? Yeah, you take the average. But what about now? I tell you that the mass of water here, of hot water, let's say is, whatever, let's say is 4. And the one of cold water, what do you want it to be? Say, you cannot know exactly right away, no one thought let's say it's 3, okay? So 3 kilograms and 4 kilograms. So let's say assuming, and I'm going to make the data easy, assuming a specific CV value. So let's say CV will be equal to 1, just to make it easy. So this is a specific heat. Assuming a specific heat CV, value CV equal to 1, determine the A final temperature of mixture, and B, if mixing process is reversible or irreversible. Oh, this is good that I do that before the equation. It's good. I'll introduce you. Hopefully we can finish it. All right. So what do you think it is? I mean, at the beginning you have cold water and hot water. You're going to mix it together. Can you get at the end again the hot water and the cold water without doing anything? No. So probably that means that once you mix it, the process is irreversible, no? So if it is irreversible, that means that the increase in entropy, the change in entropy, must not be equal to 0, must be equal to some positive value. Yeah? And in this case, to simplify, let's say here, this is insulated. So this is not heat transfer loss with the surrounding. Okay? Meaning what? That this delta Q over T here will be 0, no? Okay, because it's insulated. Right, to simplify the problem. Okay, so part A. Determine mixing temperature. Okay, of water. So over here, there's two different ways to do it, but I think this one is the easiest. Okay? If you use the first principle of thermodynamics, what do you have? Q minus work. In this case, is it any kinetic and potential energy here? No. So everything will be equal to the change in internal energy, no? Yeah? So over here, is there any heat being added to the system? No. Is there any work? No. So basically that means that the change in energy here must be equal to 0, no? Okay? So now this means that you have the change of internal energy of, let's say, cold to mixer. So this one here will have a change in energy of the cold to the final temperature of the mixer plus the one of the hot to the mixers will be equal to 0. If we make the ideal substance assumption, can we do that here? Yes, because is the water changing its state? The water is still liquid, no? Okay, so we could say that this will be equal to M cold. What will be the final temperature? Will be, let's say, T mixer minus T cold plus M hot T mixer minus T hot. Oh, sorry, I forgot something here. Sorry, guys. Don't forget here the CV, MCV, MCV. I mean, remember the ideal assumption is change in internal energy is equal to MCV delta T, no? For an ideal substance. Okay, so now this equation will give us what? This is equal to 0. So, I mean, really the CV is going to cancel out. It's not going to change anything, but. So this is going to give us what? So if we want to look at it, this will be equal to MC let's do the algebra. MC, forgot again, it doesn't matter, will be equal to M hot. I'm changing the sign, T hot minus T mixer. So let's see, this will give you what? T mixture of, something happens here, strange. T mixture of, okay, we found out this is a correct equation or not. No 100% sure now. So T, if I factor by Tm, will be Tm on MC. Oh, no, I moved that one to the other side. So M cold plus M hot will be equal to what? So you see I'm factoring out by the Tm, no? Yeah? So we have the Tm here, MC. Tm here negative becomes positive, so now that's the equation I was expecting. This should be equal to what? Should be equal to MHTH plus M cold T cold. So at the end, this is going to give us that the temperature of the mixture will be equal to what? M hot T hot plus M cold T cold divided by the total mass of the water, which is mass of the cold water plus mass of the hot water. So if we do the calculation, let's close that. So numerical application, we will give it that the temperature of the mixture will be equal to So mass hot was 4. T hot we say was 80. Plus N cold we say was 3. T cold 15. Divided by 3 plus 4. Can somebody do that calculation, please?
52.14.
How much?
52.14.
52.14 degrees Celsius.
The same as a weighted average?
Basically, that's what it is, yes. Yes. That's in the weighted average that gives you a derivation. There, it's exactly what it's a weighted average, okay? All right, so the average temperature of the mixer, so the temperature of the mixer will be 52.14 degrees Celsius. Now, part B is determine if reversible or irreversible. Okay, so over here, because I didn't do a derivation before, I'm going to kind of solve this with a kind of short derivation. So the first principle of thermodynamics is what? Q minus work, in this case, should be equal to change in internal energy. Okay? And the concept of entropy, I did not define the second principle of thermodynamics. It doesn't matter. We do it now. And what is the entropy? The entropy means that the change in entropy is equal to the delta Q over T. Okay? So these are the two basic equations. So combining both equations, and I'm going to show you how. Okay, because again, it changes a bit the notation. We have that Q minus work equal to change in internal energy. We can rewrite this one, or let's say I call this one delta Q minus delta work equal to change in energy, okay? It's the same thing. So, in this equation, using the principle of entropy, what is the delta Q over T? Is equal to T times change of entropy. So we're gonna have T delta S to be equal to the change in internal energy plus the change of work. Okay, what is the definition of the work? See, now it's starting getting a bit complicated because we combine everything, no? What the definition of work is PdV. Work is integral of PdV, but if I just take the partial, no, will be PdV, no? Okay? So now this is equal to TdS. And again, I'm doing a derivation that I will do probably next time more detailed, but will be equal to delta U plus PdV, but it's good for this problem because it will show you the understanding that you don't need to know the equation if you know how to do a derivation. So in our problem over here, what is our control volume? I mean, what is not our control volume? What is our system? System will have what? Is the volume changing of our system? No. So if it's not changing, what does that mean? dV is equal to 0, no? Yeah? So that means at the end we're going to have T delta S. And now if we do again the assumption of the ideal gas relation, this will be equal to what? M CV delta T. Correct? Alright? So now be careful, look at the map. What are we trying to find over here? We're trying to find what is the change in entropy in order to know if it's going to be 0 or it's going to be different than 0, no? Yeah? So this will give us what? Change of entropy, delta S, will be equal to M CV delta T over T. Okay, so now, right, so that's what we have over here. Okay, now let's do that step before. Now if we integrate both sides, what are we going to have? S final minus S initial will be equal to the integral of M CV dt over t. That would be equal to what? And then we're going to finish a problem, probably going to stop over here. This should be equal to what? MCV, what is the integral of dt over t? Log of t final over t initial, no? You see, this starts to get complicated now, a little bit more complicated. I mean, let me still have 7 minutes. So we can not want to finish it, but. So basically what it's saying, this, what do we derive here? The change of entropy is equal to mCV log of T final minus T initial, no? Okay? So, let's finish this one. All right, so that means what? So using previous relation, we're going to do the same thing as before. The total change of entropy should be equal to what? To the change of entropy from cold to mixer plus the change of entropy of hot to the mixer. Okay? So let me go back to the problem. In here, what's going to happen to the water? Once you mix it, the cold water is going to gain heat, no? But the hot water is going to lose heat. Correct? Alright? So, if you are gaining heat, are you gaining entropy or are you losing entropy? And if you are losing heat, are you gaining or losing entropy? So, one of them, either the cold water or the hot water, cold water or water, one of them is gaining entropy, the one should be losing entropy, no? It's not that hard to understand which one. So that's why I look over here. What's going to happen to each one of the water? So if we start at the cold water, what do we have? M cold, CV, log. What should be the final temperature? Should be the temperature of the mixer divided by the temperature of the cold. Plus, whatever change I have in entropy of the hot, CV, log, T mixer over T hot. Okay? So now I want you please to do the calculation for me for each one of these terms, but be careful here because what is M cold? M cold is 3. CV I know is 1, but here we need to do a little change. The temperature of the mixer is, what was it, 57.25, something like that? 52.14, so 52.14, but be careful here because you need to put this in Kelvin, plus 273, and the T cold is 15 plus 273. This one would be plus 4 times 1 times log of 52.14 plus 273. And the T hot is 80 plus 273. So please give me, I don't want the final result. I want you to give me first this one here, and then the value of the other one. And then we can do both of them, but. So the first one, what do you expect the first one to be? As you do the calculation. This one is the one of the cold. Should it be gaining entropy or losing entropy? Gaining. So that value should be positive, no? So what do you get on that value if you do a calculation? 0.364? Okay. So 0.364. Now, what would you expect about the hot water? The hot water should be losing entropy, no? So hopefully we get a negative value when you do this calculation. What do you get for this one? Should get a negative value. Okay, 0.329, and it's good that it's lower than the other one, no? Because what was the principle of the increase in entropy that you were saying? That this term needs to be positive, no? So this means what? That the total change of entropy will be equal to what? 0.03435? 0.035, which basically means what? This is the amount of energy that you have wasted by mixing the water. You know that this is higher than 0. So what is the conclusion? That this process is irreversible. Okay? So good thing I was able just to finish on time.